Hi, everybody. So then in this video, we now talk about the connection between linear transformations, spanning sets, and linear dependence. Unfortunately, things don't work out terribly well. It has to do with an analog to the rank theorem. Sometimes there's some collapsing that happens. So let's suppose you have a linear transformation, T, that goes from V to W. And let's say that B is just some set of vectors from V. So if B spans V, then T of B will span the range of V. In other words, if you want to know the total output, the total potential output of the transformation, what you do is you take a basis, you take some sort of space, some set of vectors that span the vector space V, and just find what T of it is. The corresponding vectors will span the range. Proof is really easy. We actually kind of used it twice already. I'll just do it symbolically this time. Let W be some vector in the range. This means then that there's some vector V so that T of V is W. That's what it means to be in a range. So if W is in the range, then there's some vector in V that's mapped to the vector W. We call that vector V. But we know, though, that the set of vectors B span the vector space V. That means there are some vectors, V1, V2 of the Vn and B, so that the vector V is a linear combination of V1, V2, V3 for some scalars, C1, C2 of the Cn. But that means that W, being the transformation of V, that's the transformation of this linear combination, which we know the linear transformation distributes through. So therefore, W is in the span of those vectors. It's in the span of V1, V2 of the Vn, the span of T of V1, T of V2, T of Vn, and so on. That means that in general, that W is in the span of when you apply the transformation to all the vectors in B. Notice I changed the theorem from what's in the book because the theorem of the book, I don't know why, it insists that B must be a finite set of vectors, and that's just not true. It could be infinite also, and the theorem is exactly the same. It's even, the proof is even the same. So then you have this result. Now, let's go ahead and try to describe the range of the transforms to get a feeling for how things work. So this linear transformation is going to be defined on the vector 1, 1 and the vector 1, 0. The linear transformation, I'm assuming, is going to go from, I didn't write it down, it's the transformation that's going to go from R2 and into P2. So to figure out what that mapping actually does in general, all I need is a basis for R2, something I know that spans R2. Well, the two vectors I just gave you, which is 1, 1 and 1, 0, that spans R2. So therefore, T of those vectors spans the range. So then that means that the vectors 2 plus x squared and 3 minus x, these two things spans the range of the range of T. And that's it. So then the range of T is literally just all the linear combinations of those two vectors. It's some scalar times 2 plus x squared plus some scalar times 3 minus x. Doing it again, I want to find out then what's the range of this particular linear transformation. To do so, all I need is some basis. So if I need some basis vectors for R2, so I'll just use E1 and E2. So I know that E1 and E2 spans R2. So I'll just apply T to each of those. So T of E1, that's where you have 1, 0. So that's where A is 1 and B is 0. You get then 1 plus x cubed. And T of E2, that's 0, 1. That would then be just where A is 0 and B is 1. That would be x minus x squared. So the set 1 plus x cubed, comma, x minus x squared, that thing spans the range of this operator T. And that's it. It's not magic at all. It's nice. That way we can very quickly figure out what's the range. Now there's some things we have to talk about though. I have not yet shown you that the range is a subspace. I'm not sure it's a subspace yet. I only know these two vectors span it. So I don't know yet if the range itself is a subspace. So I can't talk about in terms of bases yet. Also, there are some bad things that linear transformations do to linear combinations in terms of independence and dependence. Consider a really simple case. Look at the differential operator on the set of differentiable functions being mapped into the set of functions. The linearly dependent set, x squared and 2x squared, they're dependent because they're multiples of each other, is actually still linearly dependent when you apply d to both of them, because you then get 2x and 4x. Those are still multiples of each other. But if you look at the linearly independent set, x squared and 2x squared plus 1, and again, that's a linearly independent set, but then apply the operator d to them, now it becomes a dependent set, 2x plus 4x. But then if you have a linearly independent set x comma 2x squared, and they are definitely linearly independent, when you apply the operator, d operator to them, you get 1 and 4x, and they're definitely independent still. They're still independent. So we don't know when we apply the operator to a set, if the result in the beginning, if it's dependent or if it's independent. We don't know right now if in the mapping, it's going to be independent or dependent. There is one thing we can say, which I'll do another video some other time, that if it's linearly dependent, then whenever you take a linear operator and apply it to all the vectors in that dependent set, the mappings are also dependent still. It's impossible, therefore, to have a set that's linearly dependent. And then when you map them all using the operator, whatever the linear operator, whatever the linear transformation is, the resulting mapping vectors are actually still dependent. And I believe that's enough for that video.